Okay, we're going to check your prediction now. I've compressed here about 4.5 minutes of footage into just over 1 minute. So this is now running in fast time.
So as you can see, 4 of the copper flags have dropped off, and here goes the 5th. 2 of the aluminium flags have dropped off, and 1 and then just then another of the brass flags dropped off, while none of the stainless steel flags have dropped off. This is because stainless steel is a much worse conductor of heat than copper. So while it would be very hot to touch the copper rod, it's actually safe to touch the end of this steel rod here. Okay, let's turn the Bunsen off now.
Okay, so let's now try a problem. We need to come up with an expression for the rate of energy transfer in this case. So in this case, we have a rod of length L. It's got a hot side at temperature TH, a cold side at temperature TC, and there's insulation around that bar so that the only way the energy is being transferred is along the bar. Okay, in this case, we've got P is equal to Ka dt dx is our formula. Let's ignore the absolute value signs for now. So we can write this as P dx is equal to Ka dt. To work out this, we can integrate. Now x, if this is at x equals 0, then this end is at x equals L. So we're integrating from 0 to L. And the temperature at this end, we've got TH, and at the other end, TC. So integrating, we've got P, L minus 0 is equal to Ka TC minus TH. So we can write the power transferred is equal to Ka. Now remember this absolute value sign, this Tc minus Th, this is the cold temperature minus the hot temperature, that's going to be negative, so we need to make it positive, so Th minus Tc over L. So this is possibly a more useful form of this equation here. This is the one given on your formula sheet. This is probably a more useful form of it. So now there's a question for you to try. You have a bar of gold in thermal contact with a bar of silver of the same length and area. One end of the compound bar is maintained at 80 degrees C and the opposite end at 30 degrees C. When the energy transfer reaches steady state, what is the temperature at the junction? So can you work out how you'd work out the temperature at the junction here? It's a bit of a tricky problem.